So in this section of the lecture, we'll look at analyzing logic circuits. What we are interested in is three things. By the end of the section, you should be able to determine the expression, to determine the Boolean expression given a combination of logic gates or a logic circuit, and be able to evaluate a logic expression of a circuit given its Boolean expression, and be able to construct a truth table. So the first example is, let's say you have this Boolean expression shown here. Can you be able to write out its expression? So given a logic circuit, how do you create a Boolean expression? So one way of doing that is you take the expression, you begin from the left-hand side. Beginning from the left-hand side, you take the output of the gate one at a time all the way to the right-hand side. So in this case, then we'll say the output of this first gate on the left-hand side is going to be C and D. Then the next output of the second gate, it's going to be B and whatever is coming. It's an OR gate. It's going to be or whatever is coming in through the second leg. So it's going to be B or whatever is coming through the second leg, which is C, D. And then on the third gate, you'll see the third gate is A and whatever is coming through that other expression. So this is going to be simply A and whatever is coming through the other leg. So I can put it here. This is going to be B or C, D. Then it means we have our expression here, X is equal to A, B, or C, D. And so in full, then you have this logic circuit translated to this expression. Then another important issue here is to be able to evaluate an expression. So let's say we look at this expression given here. So A or B, A and B or C, D. So for this expression, when if say for example we want to ask ourselves, when does this logic circuit or particularly logic expression give us a 1? We will see that if you look at the expression here, then we will get a 1 when either sides of the AND gate are 1. So when either this side, which is A, is 1, or the B or CD and CD is 1. Thus then we can say the output expression here, let's call it X, is going to be 1 when A is 1 and B is 1, regardless of whatever C and D is. So as long as we have those as 1, then this expression will be 1. Alternatively, it can be when A is 1, C and D are 1, regardless of what the value of B is. Now, in fact, from that observation, then we can be able to construct a truth table of the logic circuit. So the way we construct the truth table, first you start off with the possible inputs. In this case, because there are 4 possible inputs, then it means then you have all of the 16 possibilities of the inputs. So now it means the output here will be 1. Remember we said this will be 1 if A, first of all, A has to be 1. So we have to look through here. This can never be 1 whenever this during this time when A is 0. So that one is out. So automatically we know this is going to always be 0. But when A is 1, your output can be 1. If A is 1 and B is 1, A is 1 and B is 1, it doesn't matter what these other ones are. Then you'll always have 1, 1, 1, 1, 1, which is that. Secondly, you will realize that also when A is 1, C is 1, D is 1, regardless of whatever B is, then you always have a 1. Then in that case, then you are able to evaluate your effect to complete the truth table for your logic circuit or Boolean expression. So then moving on to section 5, we'll look at simplification. We'll look at now how to apply the Boolean algebra laws, rules, and De Morgan's theorem to simplify general expressions. So this should be what you're comfortable in doing. So in design, you can see in this case, this logic circuit or digital system, it's equivalent to this digital system. Now, if we are going to implement a digital system, then we can see that from observation, then it would be better to implement this one as opposed to that. Simply because this particular expression uses less number of logic gates. So you have 2 logic gates achieving the same functionality of 1, 2, 3, 4, 5 logic gates. The reason is, if we know the properties of the logic gate, we know that definitely this circuit then will use less power. On top of that, this circuit will be much, much faster. So because of that, we want to optimize our design. Then it's also important, it's always important to be able to, after creating a design of a digital system, to be able to simplify it to a circuit with a smaller number of gates. So if you look at the simplification from this to that, you can see that in fact, by evaluating the output expression here, which is this, you can start with that output expression and then work our way up to this output expression in order to simplify it. So first of all, we can use the distributive law to distribute the brackets. Secondly, we can use then the observation that in this case we have A and B. So A and B, it can be represented by a single A and B. And then we have BB, which simply means B. And then we can rearrange this expression to this form. From there, then we can then use one of the Boolean algebra rules to create this, to factor out the B. After factoring out the B, we see that then we can see that A or C, it eliminates the C because then this becomes B and 1. And then from there on, we can also factor out, we can combine this and that to factor out the A. After factoring out the A, we see that we have this expression which eliminates the A, and so we have B or AC, which is a much simpler expression.